Okay, I would like to introduce my colleague Eli, and he will talk about his OVS DOCA live library.
Thank you, Aline. Okay, so let's start. Okay, we're going to talk about the live upgrade of OVS Daemon. So this is the agenda. We'll talk about the background, what is the approach of concurrent upgrade, the connection protocol, the challenges that we faced, and what are the solutions we found, the state machine, and finally we'll have a demo. So background. We have OVS Daemon that is required to handle a lot of traffic. Sometimes it needs to be updated due to bug fixes or maintenance or something like that. This requires a restart of the daemon, which has a dramatic or catastrophic even impact of the workloads. Also, it has a side effect that some states are not kept. For example, the open flows need to be reconfigured. Some other learned states has to be relearned again. And this requires a full restart, and this is bad. This is what I was talking about. It has a non-volatile database that survives a restart, like the port configuration and all that stuff. But it also has a lot of volatile state that doesn't survive a restart, like the open flows, the connection tracking database, Mac learning, tunnel neighbor, more user routes, for example. So currently, what is done in a full restart? The full restart is a sequential procedure. The current version of the daemon is going down, so we started downtime here at this point. We have the teardown of the current version. Then we have the initialization of the new instance, and then we have to reestablish all the states that we had before, and all this time from here to here is a lot of time. It has a lot of downtime. So we came with an alternative approach that to do it in parallel. While we do it in parallel, so the server, we have the server, which is the current instance of the daemon, and the client. I will explain a bit later why we call it this way. That is initializing in parallel. So the server keeps working and handling with the workloads. It is not affected at all. Now the initialization of the new instance happens in the background, concurrently with working on the current instance. They have a mutual protocol to sync the states. So all the states are synced into the new instance. Then we have a moment that we hand over the traffic from the old instance to the new instance. We reach zero downtime, and then the server, the old version, can tear down without handling any traffic. So how do we do it? Currently, we have some sockets under Varan Open vSwitch. We have the DB server socket and the daemon socket. We added another one, NDU sock, that we added. This and we introduce a new entity. We call it NDU, non-destructive update. We put it under this file and manages all the procedure of the establishment of the connection, all the states that need to be synced, and so on. And then why we call it a client and server? Because the client, the new instance, is automatically detects there is already running instance. And then instead of just failing like it does now, we allowed it to launch. And then it knows the PID of the already running process. So it just established the connection using the new socket. And this is why we call it a client. And the server, on the other hand, listens to this socket. So we have the connection established, and then states are being synced. We will show it a bit later. Still, each step of the way can fail. So, and then we are in some dangerous situation. So we have a rollback procedure. So if the client fails, so the socket is disconnected, the server detects it, it rolls back to the idle state. And then nothing is okay, so we're going to talk about a bit of the challenges that we faced. So as I mentioned, now OVS denies another instance of the daemon. If you try to do it, you will get already running as a PID something message. So we refactored some code in the daemon file to allow creation of the PID file. We have some other public API to call it from the NDU entity. And then the main procedure is changed to start first by seeing if there is another instance going, and then connecting to it instead of proceeding in the usual launch. If it doesn't, so it proceeds as usual. Now we had to load the database, the confdb. So the confdb is locked usually by the daemon. So we had to allow the new instance to access it. So the server allows it using, when we establish the connection, the server knows it needs to allow the second instance to access. There is this file that is created upon initialization, that it has a text file that holds the PID of the daemon process. So we had to, so we rename it so the new instance can also create its own file name, its own file. Then we had to sync ports. So there are bridge ports and internal ports. There are tap devices. So tap devices are ports that are between the application and the kernel. So each one of them has a tap FD file descriptor. This is received by opening this descriptor. This is the interface with the kernel. So it's used for ioctls, readv for RX, and write for TX. We cannot open them again in the client process because we will just get eBusy, because they are already used by the server process. So we use SCM writes message to pass the file descriptors from the server to the client. Then the kernel reopens them. It's a feature of the kernel. It reopens them in the other process. It assigns them a new file descriptors, and then we apply them to the tap ports, to the new tap ports on the client side. We need to open also the hardware ports, the Docker ports that is used for the two different processes. So Docker frameworks, the framework allows this capability. It manages internal priority rules to allow multiple processes. And the priority of those rules are controlled by the application, so we can achieve zero-time handover of the traffic. Next, there are the controllers that control by OFCTL. So each one of the bridges has the management port and the Snoop port. So we terminated them when we started to the existing connections. We terminate them, and files are renamed, so they are not accessed during the upgrade procedure. The port numbers, the open flow port numbers we mean, so the user can request a specific OF port request, OF port request, sorry, and otherwise they are automatically assigned. So and those are used in the open flow rules. So we had to sync those as well, and otherwise we will end up with open flows that doesn't match the correct ports. And we had to sync all those states, the TLV map for the Geneva options, for example, the meters, the groups, and the rules themselves. So what we did is all the management port of the OFCTL, we just renamed them. We didn't deny any connection. Then the client can connect to those and dump all those information from the clients, from the server side, and apply them locally. There are other volatile states like tunnel nega table, the FDB, MAC learning, and the routes. So we use the AppCTL related commands. So we implemented some dumps using the JSON format. Some of them are already in the upstream. And we also applied them locally. The data path flows themselves, we decided not to migrate them. They usually don't scale a lot, and the management of the recirc IDs is not trivial to migrate. So they are relearned and offloaded in the new client, in the new instance. City connections, we do migrate, so because it is large. If we don't migrate them, so we might have to reestablish the connection, which is painful for the workload. Since it is so large, we also manage a dirty list, because the snapshot we took when we started to migrate might change during the upgrade. So we track the new and the clear changes during the upgrade, and then we clear it in the end. And then we had we need some way to tell the system how to do it, how to launch a restart, how to launch a live upgrade instead of a restart. So we integrated into the service scripts, the systemctl. So restart is a full restart, and we took the reload word for the daemon to change it to live upgrade. I'm not going to go over all of the state machine, but you can see that this is the server side, this is the client side. So first the server is in idle, the client is connecting to it. It allows some states, some information are going from the server to the client, some information is read from the server to the client. They have some sync messages to sync all the states. And finally, both are done. So this handles the traffic. This is going down. So now I'm going to show some demo. in the other tab. Yes. Okay, thank you. So the configuration is just a standard VXLAN configuration. Nothing special about it. Those are the rules that I apply. So just for the sake of it, I use a group to demonstrate DP hash and also connection tracking that is using this group. I had some script of to show the states of some dashboard. So this is the script. I show the version of the daemon, the process ID, all the software packets that are not offloaded, and the megaflows. So this is how it looks like. We see it here. In this pane, we see all the open flows that are configured. So those are the open flows. So now, when we start traffic, we see traffic is going. At first, there are some packets going to software, but then all of it is offloaded. Now let's see what happens when we do a full restart. In a moment. So this is the restart command. So first we can see that all of it is gone. Traffic is gone at this point. All the open flows are gone, and they need to be relearned. So I will apply them again. So after all this time, it adds up to several seconds. Traffic is going back again. Now let's see the difference with the live upgrade. So notice the version, now it is 3.243. I can upgrade to number 44. So I install it in the background. Nothing is changing in the traffic. I will show the process ID. This is the current process ID. And now I launch the live upgrade. So we can see the pointer is gone. Sorry, but I don't have a pointer now, but you can see the traffic is kept going, and the process ID is still changed. So the last slide is just questions. So if you
If there are any questions, please.
Hi, thanks, Eli. That was a interesting presentation. We've sort of danced around the idea of, we'll call it hitless upgrade for a while upstream, and I know for some of the upgrade we do call like the OVS save scripts sometimes when we're doing sort of tear down restore. Is it possible we could integrate some of this functionality upstream? I think, for instance, being able to migrate ton devices so they don't tear down would be quite useful. There's probably some other state we could keep restored. So do you have any plans to put any of this upstream?
Well, currently we have a plan to upgrade to upstream Docker first because it relies on Docker. We didn't consider upgrading OVS kernel, for example, so we didn't handle all the issues that might occur there. It also has some reliability on the Docker ports that have the ability to open from multiple processes, and they have the priority. So upstreaming, parts of it may be possible, but maybe all of it requires Docker. So we have a plan to, next session is about our roadmap to upstream OVS DOCA. and then we can think about upgrading it, upstream it as well.
Hi. Yeah, they're very interesting talk. I think I have one comment that we were discussing yesterday with a lot of OVM Kubernetes people about syncing contract states across systems. So I guess even that one part might be interesting to just get some infrastructure for, even if it's not a full feature, as it would be interesting to be able to sync contract states between different nodes, like not just for an upgrade scenario. Another part I was thinking, so you said that it requires DOCA. Yeah, I guess
It's a part of it, not the connections themselves, the states of them does not, it's just software.
no, I meant ports.
Yeah.
For migrating ports, you need, yeah, you obviously need some support from whatever is managing those ports. So either it's DOCA or DPDK or kernel. So I was thinking, DPDK kind of supports the multi-process mode. So technically, it may be possible to remap some of the memory from one OVS to another. So I was thinking if you had any thought about that, or if it's even remotely feasible.
You mean to open the new instance as a secondary process, secondary DPDK process? No, we didn't consider that. We are focused on DOCA. I think it is problematic because secondary processes in DPDK, as far as I remember, they don't have they cannot detach, they cannot live by themselves while the primary is going down. But
can you maybe, I don't know, maybe it's not possible today with DPDK, but start two processes. One is primary, when you start the secondary, and then you switch one. One becomes primary, and then you tear down the other one. I don't know.
Maybe. I think currently it is not supported, as far as I know. But it's software. Everything is possible.
Okay, thank you.
Are there any other questions?
Just a note about your question. So we sync only the city state. We sync only the offloaded connections. So as you saw, we also offload the cities, the connection. So we sync only we migrate to the new instance only the offloaded ones. We don't for the ones that we don't offload, we just don't care about them.
I would have another question for the, so when the upgrade or switch over is basically complete, is there a way to go back to the old version? Like, for example, the new process crashes on handling the first packet or so. Is it then dead, or will the old one like take it up again?
If you mean after the upgrade is completed?
Yeah.
So after what? No, after the rollback is completed, so you have a new instance that is running as if you reload it, as if you restarted it from scratch.
Okay.
So if it crashes, so it crashes. So it will just reload, restart by the daemon, but the service script, I mean.
We have one question online from Alex. What is the speed of syncing of CT state? How much time you expect 2 million states will take to sync? How do you guarantee consistent of the migration?
Well, it depends on the CPUs, of course, that you run on. From the test we did on x86, it took us. Well, it also depends on how fast we can offload those new connections on the new instance. So currently we support between 0.5 and 1 million connections per second. So it might took us maybe 2 million connections can take up maybe up to 2 seconds or something like that. While this is a long time, we know that this is why we manage the dirty list that can track the new and the old ones that are being cleared during this time, and then eventually we clear on this list.
So let's thank our speaker once again.